Hello and welcome to Late Night Ambient Math. I'm your host, Ted Z. You like that intro? Okay, let's get on with it. Here's a function, y of x, and I want to find successive derivatives. I'll write it like this. Okay, so I can write it dn by dx and y of x. All right, so I'll use this notation here, which is a common notation. And I want to evaluate this derivatives at x is 0. So I want to compute the nth derivative at x is 0. This is a very interesting problem. And why is this interesting? Because it has interesting connections with discrete math and combinatorics. It's just one example of very, very many such things in calculus that have interesting and tantalizing connections with combinatorics. You know, things like generating functions, special functions, and power series coefficients. Many of these things have combinatorial interpretations and implications, hypergeometric series. It's all very interesting. It's a very, very deep rabbit hole, and I hope over time to explore bits of it with you. The first way of doing this will be by recursion. Have a look at this expression. This expression here is pretty much exactly the same thing as this, except a little bit generalized. I put a in front of the x, so a is 1 here, and b is 0 here, and p is 1/2. Okay, so we'll generalize this a little bit, and I want to take the derivative of this thing. So how can I do that? Well, I use the quotient rule. This thing, I'm sure you all love playing with this thing, u prime v minus v prime u over v squared. U is ax plus b, and u prime is just a. Okay, so what about v? Yeah, that's 1 plus x power p, and so on. Okay, so I plug all this stuff in, and what do I get? Well, I get all this over 1 plus x to the power of 2p. Okay, now I must do some rearrangements and simplifications. Here I factored out some stuff. Right, here I did the division of this thing here, and then I expanded this. So I'm going to do a bit more simplification and transformation. Look here, I can combine the terms that involve x. And I get this, but look here, this is the same thing as a. I can call that a new a, and this here is just a number, so that's a new b, and this here is just another number, so that's a new p. So I'm easily now able to find, given one step, given the nth derivative, I can find the n plus 1th derivative by just applying these rules. So that's pretty cool. Okay, let me spell out the rules. Here's the rule for an. So the nth derivative in terms of the coefficients of the n minus 1th derivative. Here's the recursion rule for bn, and notice they're mutual recursion. They depend on each other. And then I have one more. There we go. So I got pn now in terms of the previous one. Well, I need a way to start off this recursion, because recursions are like discrete differential equations. Here's your discrete math connection. So we need initial conditions. Here's our original function. So this is the 0th derivative of y. The 0th derivative of y is not 1. It's the original function. So here a0 is 1, b0 is 0, and what's p0? P0 is 1/2, because this is power 1/2 here. So I have here my 3 initial conditions, and I have my mutual recursion. It's all a done deal now. It's all sort of solved. But let's have a look at some numbers now. Let's see what the numbers look like. So I will put them in a table like this. Here are our initial conditions. Now I'm going to use these rules to calculate all these rows. Each row will depend on the previous row. It's actually a lot of work. It's a lot more work than I thought it was going to be, or that I wanted it to be. A closed form is, of course, much better, but we'll get to that. It's interesting to do these computations, so I suggest to you that you do it yourself. It's quite interesting. Here are the numbers for the second derivative. Yeah, it was pretty easy to get these numbers. Just a question of arithmetic. Derivative of order 3, 3/8, 9/4, 7/2. Order 4, we got that. And let's do one more. Yeah, we get this. Okay, so there is, this alternates. The A's and B's seem to alternate in sign, except there's a bit of irregularity in how it starts off here. But the rest of it seems completely regular. All right, but we haven't answered our question. And our question was to find the derivative at 0. So let's look up a bit. If we put x is 0 here, well, what happens? Well, this here becomes 1. This 1 plus x is 1. Now 1 plus 0 is 1. But this is 0, so this will go away. And so all we're left with is this b, this bn here, and divided by 1. So the answer to my problem lies in this column here. Let me draw that nicely. There, that's sort of better. So it's easy now to get the answer. So d5, dx, there should be an x here, dx5, fifth derivative of y of x at x is 0. This is going to be 525 over 16. Yeah, very good. I am not maybe totally happy with this solution because it's a lot of work. I would prefer a closed form solution. And I'm going to leave you with an exercise right now. Try to find a closed form formula for Bn. And it's not that hard because this recursion is not coupled in a complicated way. You'll be able to work through the maze and eventually get a formula. Now, I'm going to find this closed form expression in the next part of this vid, but I want to use a totally different technique to do it so I can show you something different. Now let me try a different strategy, the Leibniz derivative rule. So everyone knows that the derivative of a product is like this. U prime v plus u v prime. And what about the second derivative? So I can write it using my notation like this. There. How many of you knew there was a Leibniz derivative rule like this one here? Well, what about uv third derivative? You guessed it, and it's just like the binomial rule or binomial expansion. It's very similar to that, as you can see. It's very beautiful, the way it works. Right, now I want to expand this, the nth derivative of uv. Now this is a lot of writing, so I hope I can do it without messing up. Okay, that's how we begin. Binomial coefficient n0 times nth derivative of u times v, and so on. And now the this n minus 2 term here, it seems complicated, but you just practice writing this out, and it's easy to remember how it goes. And so on till the last term, nn, and now it's u with no derivative, and the nth derivative of v, kind of like the mirror image of the first term. So my function is x over root 1 plus x, and I can write it the following way, like this. And I'll define my u to be this. You'll see why. So u is a 1 plus x to the power of minus 1/2, and then my v is just going to be x. So the important thing here is that v0, that's x, but v1, that's just 1, and v second derivative and higher, that's going to be 0. So, okay, vk, the kth derivative of v is 0 when k is greater than 1. And, okay, so that means all of these terms here, all of this is all going to be 0. Well, that's really a relief, man, because now it's within the realm of possibility to figure all this out. Right, okay. And so this is what we get for the nth derivative of y of x. All those higher other terms are 0. And now let's compute this at x equals 0. So at x equals 0, this is 0. So this whole thing goes away. So that's even simpler. And I can also say that this is equal to n here. N choose 1 is n. So I get the following: n u nth minus 1 derivative at x equals 0. So we just have to compute some kind of expression for this. Luckily, that's not hard to do. U is 1 plus x power minus a half. U first derivative is this. So U second derivative is these two negative factors, and then minus 5 halves here. So you see where this alternating sign is coming from. So if I play around with this a little bit, I will end up with this expression here. It looks really formidable, but it's just a logical progression of what's going on here. So just do a few more steps and you'll see how it goes, and you'll end up deducing this. All right, so what happens when I evaluate this at x equals 0? Well, at x equals 0, this here goes away. This becomes 1 because 1 plus 0 is 1. And so I get this nice expression, very beautiful, all the way up to 2n minus 3 over 2, like this. Okay, now I'm ready to put everything together for my final answer, this thing here. So the nth derivative of y evaluated at x equals 0, this is n times this expression for u derivative n minus 1. And there we have it. There's our final answer. I think I should just specify that this expression here works for n is greater than 1. Great. So that's very beautiful. We did it. We did it. Of course, I should leave you with an exercise. Try it for n equals 5. Do you get 525 over 16? I somehow wrote 526 over 16 in the earlier part of the video, but it should be 525 over 16. So do you get that for your b of n? This is b of n when n is greater than 1. You should get that. Well, there you have it. I hope you found this interesting. Please click like, comment, and subscribe. And if you really, really like this video and you really like this topic, then send me a super thanks. I'd like to point out that there are many, many worse ways you can spend your money than supporting mathematics online. Okay, this has been Late Night Ambient Mathematics with your host, Ted Z. And stay tuned for the next episode. I will see you next time.